everyone, welcome to the second lecture on general troubleshooting of electronic circuits. In this lecture, we are going to cover 8 steps of troubleshooting process. In the last lecture, we discussed the definition of electronics troubleshooting, and then we covered some topics like fix versus repair, fault and symptoms, precision and accuracy, and all those were really important. When you troubleshoot, you should know those terms. And at, and after that, we briefly saw all these 8 steps of electronics troubleshooting. So now in this lecture, we are going to get in detail of these steps. We are going to talk about each stage in the troubleshooting process. So starting with the background. So in the background, you should know what the circuit is supposed to do. And to know that, you need to gather the information, which is the first step in any troubleshooting. So you need to ask yourself different questions. For example, what technical documentation about the equipment is available? You should ask, how exactly is the equipment supposed to operate? Are there any previous lessons learned? Review any material history that exists for the equipment. Identify similar equipment to which you can compare the manufacturing malfunctioning equipment. So all these questions you should keep in mind as you begin to gather the information, and that will create the background of the problem. So you need to have a framework, and this is called your framework, where you know the information about the circuit and what are the each components used in the circuit. So that when you have that knowledge, then that creates your base, and that's your first step. So it says the same thing: research information on the things you are troubleshooting. It worked fine yesterday, and now what happened, and what would be the reason? So that's the first step. Now in background documentation, what do we have? We have schematics, we have block diagrams, user diagrams, manuals, technical support. So these things include under documentation. Schematics, you all are already familiar with it. You have been making electronic circuits, and this represents this is one of the example of a electronic circuit schematic, where if you see that this red box is used to basically divide the circuit into 3 parts. At the center, you see we have a microcontroller, and then we have here a sensor, and then from here we have some supply coming in. So this, you see VCC, so that's a power supply and the controller, and then you have a sensor. So we have divided the circuit into 3 parts for this particular schematic. And as you do the troubleshooting, you can study each part of the circuit separately and see what input you are giving to the circuit and what output you are getting, and is your output is what you're expecting, or if it is deviating from what you expected, then how much it is deviating, or is it totally off the reading, and if it is totally off, then you have to get into that particular portion of the schematic or circuit, and then troubleshoot what happened in each component. And the same process you will do for each component. For example, like measuring input and output, and seeing if they have you're using the same rating. So that kind of stuff you will basically find out. So moving on, now you have this block diagrams and flowcharts. These are very helpful in detecting the in basically creating a plan to troubleshoot, and you basically use this flowchart to see how how your circuit is working. So starting from power supply, which is connected to the sensor. So this is just an example, and then in between this is connected to computer, and from computer you are getting some output. So this kind of flow chart. So in short, you basically get the big picture of the circuit you're working on. So it's a good approach to create a block diagram or a flow chart. So this is an example of a flow chart, and in this, for example, you have some system which starts, and it has two options: system started, yes or no. And then based on these two responses further, your flow chart is basically created, and you basically find out what the problem is there in the system and at which step. So for example, let's say there is no problem until here. So after each block you are giving yes response. So system starts, yes. Windows boots, yes. Error message on main screen, let's say yes, and then goes here. Module display correctly? No. So if you say no, then at this point you know that something is wrong in between here. Till here things were working fine, so something wrong is in between these two steps. So by that so by doing this approach, you save time. You don't have to go through all till the end step, because you at this step only you know that things are not fine here, and the result you are going to get further is going to be wrong. Okay, so this way you basically understand the circuit using the flow chart. And manuals and technical support, which includes utility programs, user manuals, service manuals, technical support. So yeah, these are basically your documentation about the circuit, how it works, how much power it has, different ratings it can support, the components included, their rating and stuff, and how they should perform. So those performance characteristics, and that stuff is basically included in these technical support report or manuals. And based on this, you know that you have a good amount of information about the circuit, and then you can move forward to next step in this troubleshooting process. So background questions which are important to answer. Do you know enough to repair it without breaking the first rule? So what was the first rule? The first rule was not to harm yourself, and that's the main rule you should follow when you are troubleshooting. So do you know enough? Do you know enough to repair it without breaking the first rule? That means you should do your homework in terms of understanding the circuit, and if you do that, then you won't be breaking the first rule. Do you know what you think you know? So here also covers your all the technical manuals to understand the circuit. How is the customer using this? Are they using it differently than I expected them to? So yeah, this is also an important question, because sometimes customers, they don't know, or users, they don't know how to use the particular circuit or equipment, and they use it differently, and that causes malfunction. So it is important to ask the person who was using that circuit or using that equipment, and see if they used it in the way which is specified by the manual, or they did something wrong, or different process they use. So here it is important to ask those type of questions. And moving further, has the customer had this problem in the past? So that will tell you, like, is it a frequent problem, or is it intermittent for a problem? So asking these questions are really good. What kind of maintenance has been done? Who last did the maintenance? Asking these questions are also important because by these questions you get to know, like for example, if somebody already did the maintenance, then did they change any equipments in the circuit, or did they redid any soldering in the circuit. So those kind of concern, basically you get to know asking these questions. So this is important. And then are you aware of common failures of this product? So now here comes the product information. There are some products which basically do not respond to particular ratings or particular environment. So once you have this background information, you will know that yes, this particular equipment will not perform in this temperature or in this environment, or if it is used for these particular number of years, then its efficiency is reduced, or any motor you're using, so that will not going to work pretty well after a certain time. So those questions can be answered once you know the technical detail. And then explicit versus tacit knowledge. So explicit is that knowledge that can be documented or explained. Tacit knowledge that is used from intuition or a hunch and cannot easily be expressed. So you want to have the explicit knowledge when you're working with the circuits. Having the hunch knowledge is good to an extent, but if you're really troubleshooting electronic circuits, then you should know the documentation, and you should be able to explain what is happening in the circuit. So next is tools. So this troubleshooting process, it involves checking the terminal voltages across the components and devices in the circuits. It checks for continuity of the current, looks for any open circuit faults or short circuit faults, measure the resistance, capacitor, transistor, inductors, and their status, whether they are functioning or not. And for that, you can use some of the tools, for example, analog and digital multimeter you can use oscilloscope, LCR meters you can use, variable power supply with metered indication you can use. So there are different tools which you will use based on the troubleshooting problem. And let's read here. Not every problem is solved with the same instrument, but all problems can be solved with an appropriate applied tool. So it's important you need to know what your problem is and what type of tools it will require. So this is important to know, and based on that you can detect the tools. Tools, precision and accuracy. Make sure you're using the right tools for the job. Common tools which can be used, as I mentioned before, digital or analog multimeter, you can use oscilloscope, LCR meters, variable power supply with a metered indication. Don't use a rule to measure miles. Don't use an odometer to measure inches. So at the end, it's saying the same thing, that you should use the correct tools to measure any quantity or any fault in the circuit. For that, use the right tools. Primary test equipments include sight, smells, sounds, heat. So look for these signs and see. So these steps, these also involved in getting physical contact with the circuit. So it is better to first remove the power supply to the circuit and then wait for some time to discharge a current in some components, so that you can hold it without fear. So and then if you don't want to, if you don't go with removing the power supply first. Without that also you can basically detect if something is going wrong with the circuit by its by smell, by sound, and sometimes heat flames basically goes up, and you can actually visually see that, and then usually the immediate response is to turn off the power. So check for any exploded or burned parts of the circuits by seeing or smelling them, and look for any loose connection. Check for any ground paths. You can, in case of printed circuit boards, you can look for any overlapped traces, and you can also observe the soldered points, whether they are correctly soldered or not. Check for any shorts or touches on the adjacent soldered joints. So these are some of the things you can look for in the when you are troubleshooting the circuit. So it's the same thing which I mentioned. Observe the so check the blown and burned pieces of the circuit, look for loose and poor connection, check for overlapping tracks on the PCB, observe the solder parts, whether or not they are properly soldered. Check for shorts or keys on the adjacent soldered points. Now power, is it plugged in? Power is not just the supply but all the inputs: signal, air pressure and volume, fuel level, etc. So all these include into your power. So you need to see if your power is on or is it off, and make sure before you before you touch the circuit, uh, you should first have all the tools, and then you should first turn off the power and see if everything looks okay or not, and then try to understand the circuit, what is happening there, and then if necessary, then you can basically first check for the power supply, and then give the power supply to check for things like, as I said before, continuity test, and you can check the voltage across the components. So those kind of stuff you can check. So let's read here. It says, don't forget to look for inputs from previous stages. Signals and material flows need to be present. So yeah, as I said in the beginning, that you can divide your circuit into blocks, and you should see whether you are getting the right input, right output from the previous stage. So this is important, and this troubleshooting actually you can do it component wise also, like each component attached. At the output of that component, you can see if you're getting the right amount of current or voltage. Okay, so next is performance versus specifications. So in this, you need to know the answers to these questions. Let's read it here. What is it doing that's it's not supposed to do? Can you duplicate the failure? What is it doing that it is supposed to do? Can you make the failure worse? Is it functional but the operator not using it right? Is the operator trying to get it to do something that it's not supposed to do? So look for all these signs. So in short, look and listen, and that includes what customer says or what the customer does with it. So you need to note any burned areas, dusty areas, lubrication, belts, any belts in the circuit that does not fit correctly, any fitment issue, alignment issue of mechanical and electrical connectors. You should also note for any circuit board missing parts. If something is missing, see if there is anything unused or unopened in the circuit. Okay, so look for these signs. And next is so yeah, it's the same thing. It's just a saying: compare apples to apples, duplicate conditions, design for experiments. It's built logically, step by step. So Check that all inputs are appropriate to the block. Check the preceding and the succeeding blocks in the circuit, and sometimes there is signal present, and just because of that signal present between the previous and the next stage does not mean that the input is still correct. So look for those signs when you are troubleshooting. Now next we have is the localization. So in localization, you eliminate any obvious non-problems. For example, if you see there's any component which may not cause any fault, or which has lower chances of causing any fault, or does not show any symptoms. So you should know what do you know is not causing the problem in the circuit. So that's also important, and that you already do in the labs also, like you check on the components which are doing fine, and by that you know that what portion of the circuit is working fine, or how many components are doing okay. So that's important to know. Now, and in this localization you should also check for customer modifications, if there may be a reason that something is connected incorrectly and that may be causing a problem. So look for that. And then you have localization procedures. So these are the different ways you can do the localization: sequential analysis, splitting, input output relationship, known good replacement, substitution, where you substitute the old component with the new one, no high failure rate and wear components. So these are some of the procedure you can follow. So these looks pretty easy to understand: sequential analysis, half splitting of the circuit, input output relationships, we little bit briefly discussed, and then replacement of the component, old to new, and then look for any components which has higher failure rate, or if there is any wear or tear in the component. Localization, input output: if I do this, then then it should do that. If I do this, it does that. If I do this, it does that sometimes. So these questions you would be able to answer when you do when you start troubleshooting with the tools, with the right tools, and check for that. Then you should have these questions in mind, that what you are doing and what you are getting, what you are giving to the input, and are you getting the right output, or does it matching with what you are supposed to get, or what the output if you're getting is it by chance you're getting, or is it like constant. So look for those signs, and in generally we tend to look at what we know, and if you know how to hammer everything, gets treated like a nail. Next is localization procedures. So this one is sequential analysis. So as it says, step by step, walk through what it's supposed to do in the orders it's supposed to do in the circuit. So in your circuit, maybe starting from the power supply and further to the main body of the circuit, and then to the output of the circuit, something like that. So step by step process, 1 2 3 4 till 8 given. So let's see what it says here. Load component from tube, test current, reject if out of specification, program target device, verify program load on target device, reject if verification fails, orient program device for install an subassembly and solder, automated AC test, automated AC test. So this is just an example which has been given over here, and it could be different for your circuit, but just do step-by-step analysis, and if you do that analysis, then that's called your sequential analysis, and that's one of the method of localization procedure. And then this is another way doing the half splitting. So if you half split and then check whether the circuit is doing okay or not, and keep on checking. So splitting the half circuit and doing the sequential analysis. Known okay here and known failure here. So start in the middle. Is everything okay? Check from here and then work backward and so on. So no, at this in this stage the fault is in the preceding stage. Yes, the fault is in the following stage. So basically at this point you will get the answer whether you are if you're getting the right output here, then you will just move forward and then check the next stages. If you're getting the wrong answer, then you will go back to the previous stages. So that's how half splitting works, which starts in the middle and work towards the fault. Localization, input output, we already discussed. You for each stage you basically check input and output. Black box approach, treat the stage as a black box, change what goes in and look at what comes out. Is it what you expected? So change the input and see what you are getting at the output. By that way you will know what is if the particular stage or for a particular block is performing correctly. So that's your input output localization. Localization procedures, known good replacement. So if you have a new part, one that has been tested, can you swap that part out with the suspected part and change the problem? And this you already do most of the time in the lab. If you have a new part, then you replace with the old one and then you test it out whether the circuit is performing correctly or not. So that was your known good replacement. And you also need to know if there are sometimes some components which have higher rate of failure, like in microcontrollers. If you provide higher voltage, then it might basically not perform the way you might think and may burn up, and that same can happen with op-amps also. So you should know which components are sensitive and they have higher risk of failure. So swap out the components that are known to go bad, even if you don't even if you don't know whether that component is bad or not. You can replace it and replace with something, replace with the new one, and then see the performance. So previous one was if the component was bad, then you replace. But in this case, you replace the component which you know that they might fail. You don't have the enough information, but you think that that particular component might fail, so you replace them. So swap out the parts that are known to go bad. If you have had a problem with a particular stage in the past, it might be worth checking. Replacement, known good, also a way to localize. It's called a shotgun method, and if you can't isolate to a particular part, replace it and several of its friends. That means if you are not able to find that particular part, then any closest to that part, so that you have to check through the data sheet if the ratings are matching. But this is an expensive approach because you're replacing the part, and some parts may be expensive to replace. So we try not to do that. We prefer to troubleshoot the circuit and try to fix that way. So that's your last resort of replacing the parts. So that's the replacement. And then check again the performance versus specification. So go back and recheck your results, what you got after doing all those steps, the previous steps, and go to step 5. And step 5 was your again performance versus specification was the fifth step. Do that, and other steps are possible. You may have determined a need to go back to research more information, get a different tool, recheck power or supply issue, etc. So you go back to the 5th step and then do the recheck your the results you got. Okay, so performance versus specification. You then do this localization and then see if you have to do the replacement or not. Okay, so documentation, process of closing the loop so that new design can avoid old problems. So documentation is very important in troubleshooting. You must include whatever the information you got about the equipment, so that in the new design that problem can be avoided. And also for some other technician, it's good to refer to the old documents when they are troubleshooting to see like what happened to the equipment or that kind of equipment. They often get these issues, so that knowledge is important. So tactic knowledge can become documented. Components that don't meet specification are used for supplier feedback. So any components which do not meet the requirement of the circuit, they can be replaced, but that information, how that can be documented, that can be documented when you troubleshoot the circuit. And you once you do that, then you need to write that down for future use. So that's all in the electronics troubleshooting circuit. So always remember all these steps, and at the end, documentation is super important. Your findings are crucial to what troubleshooting you are doing, and you have to include all these information, document whatever the circuit you are troubleshooting in the lab, in your report. So that's all for today. Thank you so much for watching.